working in the lab late one night when my eyes beheld an eerie sight. For my monster from his slab began to rise, and suddenly, to my surprise,
he did the mash.
He did the monster mash.
The monster mash.
It was a graveyard smash.
He did the mash.
It caught on in a flash.
He did the mash.
He did the monster mash. To my love Notari in the castle east, to the master bedroom where the vampires feast. The ghouls all came from their humble abodes to catch from my electrode.
They did the mash.
They did the monster mash.
The monster mash.
Okay, that was really scary. That was my bobblehead doll. Woohoo! I had gotten into a shrunken head due to all this wild and crazy thing. I almost got eliminated, and you would have had that substitute teacher, my little bobblehead doll, which my wife got me for my birthday one year. So it's very, very scary. So just thought I'd get us started off on the right foot, have some fun with this, and start thinking about E1, anyone. So now, just like when we were doing SN2, we played with SN2 for a few lectures and then dabbled in SN1 because it's chaos. The same chaos is going to occur in this video as well. E1 can't stop being chaotic. You might think it's going to go by the same thing that, let's make sure I got this right. There we go, right pen, red, scary. What do you think about all this E1, E2 mechanisms and how they compare to SN1, SN2? They gotta be very, very similar. So as we saw with E2, both the leaving group and the base, just like the leaving group and the nucleophile are involved in the rate determining step. And E1, it's going to look a lot like SN1. Notice the leaving group on the slow step just pops off. That's the same thing about SN1. So we create this tertiary this three bonded carbocation. Wait, you sure you don't want to just step in for a minute? And okay, sorry. He's kind of freaking me out. I should hide him somewhere. So we create this carbocation, a very, very unstable carbocation. Notice in this process, there's no base, and there's a very poor nucleophile, if any, for this reaction to go by. Okay, so these are really kind of the same stories and all the same chaos that occurred with our carbocation in SN1, all that same chaos of hydride shift, methyl shift, resonance rearrangement, carbocation rearrangement, all of that can take place in E1 as well. Whew. All right, so unimolecular elimination, you can see here there's definitely no strong base up here. I have a very weak nucleophile in ethanol, and now that you're aware that you can form an alkene, loss of a beta hydrogen is essentially in that last step. Basically, the loss of the beta hydrogen is like the molecule just eating its own arm. I want a pair of electrons. There, I got it. To form this E1 product, or it waits around for the SN1 product to occur. So now every time you do an SN1 reaction, I'd like you to tell me, do you have the SN1 or E1, and which one is the major product? So who's major when we do these? Do I have a major, or do I make these in a 50-50 mix, or what's going on here? So this is what has go away, little guy. This is what we have going on in lab. We have seen in lab that if I write the reaction like this, nothing under the arrow, or I might even write 25 degrees Celsius or RT for room temperature, if I have that going on, and I'm going to erase that because something's going to pop up there. So if I have RT, room temperature, going on, then really the major product is going to be major the SN1. And therefore, and the elimination will be the minor. It's harder to break and make that pi bond at room temperature. But if I give you a little heat and add some heat, this delta symbol that I was making room for, if I write heat for this reaction, then what we found is the E1 product is preferred, and that you would write the E1 as the major. And this is the minor, SN1 with heat. So you can do a little control. It's mostly on paper because in all reality, notice the percentages still give you a mixture, a mess. You get the SN1 product and the E1 product. So it's a messy, messy situation when you get to a point of SN1 or E1. But keep in mind, you will never have competing SN1 E1s with SN2 E2s. Those two require a negatively charged, great nucleophile, strong base. Nothing ever going to see that in an SN1 or E1. All right. Any surprises to this E1 mechanism? Just a little bit. We were so worried about getting the leaving group anti and coplanar to the beta hydrogen in an E2 reaction. And that's because the bulk of the leaving groups on one side. And if you remember the Newman projection, it was great. They could be anti to each other and no steric hindrance involved. But notice what happens in this E1 mechanism, that the leaving group falls off. It's gone. And so you got this 3-bonded carbon with a positive charge that's incredibly uncomfortable. And therefore, its p orbital that it's going to use to make a pi bond will go in any direction it can just to make the pi bond. So at this point, this will line up perfectly. Any one of these hydrogens will line up. It doesn't even matter. This is an empty p orbital, empty on top, empty on the bottom. Give me a hydrogen with a pair of electrons, anything at all, just so I can become a nice, happy 4-bonded carbon. So no worries, no anti-coplanar. It's like the only nice thing about E1 is you don't have to worry about the leaving group and the beta hydrogen being anti and coplanar. It really is the only thing nice about this reaction. Okay, so here's the review. It still follows Zaitsev's rule that when it tries to fall apart, I can look around, and you should. Here's the leaving group. Nearby, I have beta hydrogens here on a primary carbon, and a secondary carbon. So look around at all the beta hydrogens, because at room temperature, you're still going to make the major product is going to be the SN1 product, and the minor will be the alkenes. But you throw a little delta symbol in here to indicate heat is being used in this reaction, and these switch. And therefore, the more substituted, the Zaitsev product is going to be your favored product here, okay? And the minor product will be SN1, and the least substituted would be even more minor, okay? So write them all out, classify them if you want, just to show me that you are aware that there's chaos, absolute chaos taking place in an SN1 reaction now, because E1 will always come along for the ride. It'll either be a minor product or it will be a major one if you use heat, but it'll always be in your products. I know, frustrating, but it's nice that it follows Zaitsev's rule and will still follow Hoffman's rule if you want to make the less substituted alkene as well. What about chairs? Do we still need that trans-diaxial paraplanar still apply? What do you think? No, yeah, you're right. No, as soon as you make that carbocation, the leaving group is gone. So if we make the carbocation, there is no need to worry about the hydrogen being beta or anti, because to tell you the truth, this is no longer a chair. It'll lose its chair configuration at this point because you have a 3-bonded carbon. And therefore, why does it need to be in a chair and make sure it's tetrahedral? And no, that's gone. It's got empty space all around that 3-bonded carbon. So it will fall out of the chair a little bit and just try to align with any beta proton it can and eat one. Eat a pair of electrons off itself to create the major and the minor product here. Oops, where'd it go? There we go. So it will just do anything it wants because of this trigonal planar carbocation. Still creating a mess of crud. I didn't even draw them out because I'm just annoyed with it. But with the heat symbol, then I want to draw the major product and focus on this one, which is the Zaitsev product. And that's what you'll always make in an E1 elimination with a chair or even any other aliphatic carbons. Cool. Trying to point out the highlights to this one reaction. The lowlights are that there's lots of chances for rearrangement, multiple products, SN1, SN2, no SN2, excuse me, SN1, rearrangements, chaos. So let's narrow the chaos a little bit. See if you can show me in class, draw out the reaction mechanism, arrows pushing everywhere, for how this product was formed using only these reagents and these temperature conditions. Okay? And make sure to show me every arrow for every bond formed, every bond broken, and that's how you know you've gotten the reaction mechanism. I also want to make sure you're clear, oftentimes the product of these reaction mechanisms are not always the major product. Sometimes I'm trying to get you to see how would you make this minor product. So don't worry so much about if it's a major or minor product. See if you can actually just show me how this product is generated using arrows for electron pushing. Okay? All right, there we go. Now we're done with E1. Hopefully this is all coming together for you. Please ask me lots of questions. I love questions. And besides, freaky little Nick bobblehead might be the one that comes and answers them. Woo! Okay, sorry. Gotta put that little guy away. Scaring the life out of me. All right, have a great day. I'll see you soon. Bye.